time to figure out how to get a value for that constant of integration. What we need to know is what point does the antiderivative go through? And I'm going to show you what that looks like in just a second. All right, so we are going to get an actual value for C. Remember, a constant is just like when you add a constant that just changes the vertical shift of the graph. It doesn't change the shape. So what I got is we want to find the constant, the particular solution. So the antiderivative with a value for C that has the initial condition of f of 1 is equal to 0, and the derivative is 1 over x squared. So I'm going to start with, we're going to do this the official way. So the derivative is dy dx is equal to 1 over x squared, which we know is x to the negative 2. I'm going to multiply both sides by dx. This is how we get the dx in our integral. So I get dy is equal to x to the negative 2 dx. And when I want to undo the derivative, the change in y, I'm going to undo the change in x. So what I get is the integral of dy is y, and I need to take the integral of x to the negative 2, so I do x, the negative 2 raises to the negative 1, and then I need to divide by the negative 1, plus c. So I have y is equal to negative x, negative 1 over x plus c. And instead of y, we call that f of x, okay? All right, so I am going to show you what this looks like on Desmos. I have my function 1 over x squared. That was the derivative. Then my original, when I took the antiderivative, is negative 1 over x plus c. So the derivative, the red, shows me that the outputs are positive, which means that the slopes are positive. The graph is increasing. The slopes are positive. It starts off increasing very slow, and then the slopes are going to get really intense because they're getting higher and higher. Okay, we're starting high on the next arm, so the slopes are really steep, positive steep, and then they get close to 0. Okay, so or they get close to 0. Okay, so what I have here is if I have a constant c that's 0, I can see that the function has positive slopes, positive rates of change, and they are getting steeper and steeper as we go. On the right-hand side of 0, they started off very steep. They're still positive. The outputs are negative, but the slopes are positive. And as we get closer and closer to infinity, the slopes are leveling off towards 0. If I change my c value to like plus 3, okay, so it goes plus 3, it's going to go through 0, 3. No, it doesn't have a y-intercept. Just kidding. Okay, so I'm going to add plus 3. It's going to shift my graph up 3 units, but it doesn't change the shape. I can still see that the slopes are increasing slowly, then really quick, and then on the right side of the x-axis is they're increasing really quick, and then leveling off, just like we saw in this function. So it doesn't matter where the shift doesn't affect my antiderivative. So in order for us to figure out what the c value is, we need to know a point that the graph goes through. So luckily, we have that point. Okay, we have that the graph is going to go through the point 1, 0. So if I change, actually, let's just solve for it. So what I need to do is just plug in to solve for C. I plug in f of 1 is equal to 0. So I get 0 is equal to negative 1 over, I use this equation, negative 1 over 1 plus C. So C is equal to positive 1. And then I write my particular solution. So the particular curve that goes through the point 1, 0 is f of x is equal to negative 1 over x plus 1. That's my C value if I go through the point 1, 0. So let's go back to Desmos and check it out. Let's change our C value to 1. I think I can actually just, okay. And now I'm going through the point 1, 0. So the equation here would be negative 1 over x plus 1, and it should give me the graph that goes through the point 1, 0. If I have some other point, like it's going to go through the point 2, 0, then it's going to have to be a different C value. Okay. All right, let's move on to the next example. Let's find my next example. Okay, so we're going to find the particular solution of the given the following conditions. So the double derivative, second derivative is 2x plus 3, and I'm given an initial value for the first derivative and an initial value for the original function. So I'm going to take if I have f double prime of x is equal to 2x plus 3, what I want to do is take the integral giving me f prime of x is equal to, we're going to raise the x. So we start with 2x. We raise the x from the first power to the second power, then divide by 2, plus 3x. It was to the 0 power, so now we're going to add a 1. So I need to divide by 1, and I add c. I get f prime of x is equal to x squared plus 3x plus c. And then we're going to solve for our c value. I know that f prime of 2 is 8. So to solve for c, I'm going to set y is equal to 8, plug in 2 for x, and solve. And I got c is equal to negative 2. So my particular solution of f prime of x is equal to x squared plus 3x minus 2. Okay, now we're going to solve for the original. F prime of x is equal to x squared plus 3x minus 2. So again, we're going to take the integral, pop on our dx. Okay, so I get f of x is equal to, raise the power from the second to the third, then divide by 3, plus 3x, raise the power to 2 and divide by 2, minus 2x to the first power and then divide by 1. So, and then add c. I now solve for c by looking at my original conditions. There you go. F of 2 is equal to 0. So we're going to plug 0 in for y and 2 in for x. So 2 to the third over 3 plus 3 times 2 squared over 2 minus 2 times 2 plus c. Okay, I get 0 is equal to 8 over 3 plus, okay, one of those 2's is going to cancel, so 6, which is 12. Let's see, 6 minus 4 plus c. So I get c is equal to let's see, this gives me 2. So I'm going to do negative 8 over 3 minus 2, which is negative 8 over 3 minus 6 over 3, which is negative 14 over 3. Yeah. Okay, so my particular solution is f of x is equal to x cubed over 3 plus 3 over 2x squared minus 2x minus 14 over 3. Just double checking my work. Okay, and last example for today. We're going to throw a ball up in the air, and the initial, oh, this is not the last example. This is the second to last example for today. Okay, we're going to throw the ball up in the air. The initial velocity is 64 feet per second at an initial height of 80 feet. And we find the position function. We're going to find the position function giving the height as a function of time. Next, find when the ball hits the ground. What is the velocity of the ball when it hits the ground? Use A is equal to 32 as the acceleration due to gravity. So I got a lot of information here. The initial velocity is 64 feet per second. So V of 0 is equal to 64 feet per second. Other given information is the initial height. So I'm going to use x of t. So x of 0 is equal to 80 feet. And what I want to find out is when the ball hits the ground and what is the velocity of the ball when it hits the ground. Okay, and then it also says that a of t is equal to negative 32. Okay, so a of t is equal to negative 32 feet per second squared. So how do I take the antiderivative? Well, guess what? We're going to take the antiderivative of negative 32, and we're taking that with respect to time. And when I do that, I'm going to end up with the velocity. So I get v of t is equal to negative 32. That's t to the 0, so this becomes t, plus c. I can solve for c by knowing that v of 0 is equal to 64. So 64 is equal to negative 32 times 0 plus c. So c is equal to 64. So our particular solution is v of t is equal to negative 32. T, replace c with 64. All right, that's number 1. But I know that I'm going to have to find the height because it says when will the ball hit the ground. So when the height is 0, basically, okay, when are we hitting the ground? So the next part is for me to find x of t. X of t is going to be the integral of v of t. So v of t dt. So x of t is equal to the integral of negative 32 t plus 64 dt. So x of t is equal to negative 32 t squared over 2 plus 64 t over 1 plus our constant c. Now this constant c is a different constant than our velocity, so we're going to call it constant 2. All right, x of t. Oh, and then now we're going to solve for c of c2. Okay. I know that x of 0 is equal to 80 feet. Okay. That's our initial height. So I'm going to plug in 80 is equal to negative 32t times 0. Anywhere there's a t, I'm plugging in 0 plus c2. So c2 is equal to 80. So our particular solution is x of t is equal to negative 32. Oh wait, negative 16 let's simplify that. T squared plus 64t plus 80. And we're going to save that in our back pocket right now. All right, so now we're down to like our real work. So when does the ball hit the ground and what is the velocity when it hits the ground? So we know the ball hits the ground, hits ground, when x of t is equal to 0. So I'm going to plug in 0 and solve for the time. I'm going to use my math. Factor out 16, giving me negative 16, giving me t squared minus 4t minus 5 is equal to 0. I already have the 0, don't need that. Factor, let's see, I'm going to divide by negative 16. So I get 0 is equal to t minus 5 times t plus 1. So t can equal 5 and t is equal to negative 1. Negative 1 is not in my domain. So when the time is 5, the ball hits the ground. Okay, that's part 1. And then it asks me for the velocity of the ball when it hits the ground. So now we're going to use our velocity equation. So the velocity when it hits the ground is v of 5, okay, is negative 32 times 5 plus 64. So v of 5 is equal to negative 96 feet per second. Done. All right, next problem. And then this one's for real, the last one. A particle moves along the x-axis at a velocity of v of t is equal to t minus t 1 over t squared. At time t equals 1, the position is x equals 3. Find the acceleration and position function for the particle. When is the particle at rest? When is the particle moving left? When is the particle speeding up or slowing down? All right, so I always look at like if it gives me a position, I can see that x of 1 is equal to 3. So 1 comma 3. I'm going to find the acceleration, the position, I usually number them, and then when is the particle at rest, when is the particle moving left and right, when is it speeding up, when is it slowing down. 6 things. Just little things, no big deal. Okay. So we have the velocity of t is equal to t minus 1 over t squared would be t to the negative 2. I'm going to go ahead and find the acceleration first since that's just the derivative. Okay. So a of t is equal to, don't forget how to take a derivative, 1 times 1, and then you reduce the power, so t to the 0, minus negative 2, so that becomes positive 2, t to the negative 3. So the acceleration is equal to 1 plus 2 over t cubed. Part 1, done. Okay, time for the position. So the velocity is a derivative of position, so I need to take the antiderivative to find the position. So v of t, actually we're going to take the antiderivative of v of t dt to give us my position. Okay, so I get x of t is equal to the antiderivative of t minus t to the negative 2 dt. So position is equal to, okay, I take the t, raise to the power squared, and then I divide it by the power. Minus t to the negative 1 over negative 1. And I had 1's in front, so I don't need to bring forth the coefficients. Plus my constant of integration. So I get x of t is equal to t squared over 2 plus 1 over t plus c. And then let's go ahead and solve for our c value, which is, I know that at x of 1, we have a position of 3. Okay. So I'm going to go ahead and plug it in. 3 is equal to 1 squared over 2 plus 1 over 1 plus c. So c is going to equal 3 halves. So x of t is equal to t squared over 2 plus 1 over t plus 3 halves. I think I better highlight these. There's number 2. There's number 1. Okay. Now we're going to figure out when the particle is at rest. So particle is at rest would be when the velocity is equal to 0. So when is the velocity 0? So luckily I have the velocity function. V of t is 0. So I can put 0 is equal to t minus 1 over t squared. I'm going to add 1 over t squared to both sides. So 1 over t squared is equal to t. I'm going to cross multiply, giving me t cubed is equal to 1. And the cube root of t cubed would be 1. So the particle is at rest at t is equal to 1. Highlight part 3. Part 4. It says, when is the particle moving left? Okay, moving left. That is when the that is when the velocity of t is less than 0. Remember, the velocity of t is less than 0. So looking at my velocity function, I have critical numbers, t minus 1 over t squared. I have critical numbers at t is equal to 1 from when the particle is at rest. And then I can also see that I have an undefined value at t is equal to 0. Okay, so drawing myself a number line, I get 0 and 1. I'm going to test that for v of t. So let's test some values. I have v of negative 1, v of 1/2, and v of 2. And I end up with negative 1 minus 1 over negative 1 squared. So negative minus a negative gives me more negative. Okay. And then 1/2 minus 1 over 1/2 squared gives me 1/2 minus 1 minus 4, which is definitely a negative. Okay. And I'm just going to put an open circle here because we're undefined at 0. Okay. And then v of 2 would be 2 minus 1 over 2 squared, which is going to be a positive since it's 2 minus 1/4. Okay, so positive. So I am moving left, moving right. I'll just put left, right. So we're moving left between negative infinity and 0. We're at rest at 0. Then we move left again from 0 to 1. We move right. It didn't ask you for this, but I'm going to put it from 1 to infinity. Okay, last part is the slowing down and speeding up. So just so you know, we speed up when the signs match. When the acceleration of t and the velocity of t have same signs. So both negative or both positives. We slow down when a of t and v of t are different signs, right? So we have to find out our critical numbers for a of t, which is 1 plus 2 over t cubed. I can see right now that I have a critical number when t is equal to 0, since it's undefined. And then let's set a of t equal to 0. So 1 plus 2 over t cubed. We'll subtract 1 from both sides. So negative 1 is equal to 2 over t cubed. Cross multiply. Negative t cubed is equal to 2. So t cubed is equal to negative 2. Take the cube root. So t is equal to the cube root of negative 2, okay, which is about equal to negative 2 to the 1/3 power, negative 1.25, da, 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 da. Okay, so let's set up our number line. I have negative 1.25 and 0, and we're undefined at 0. So I tested the values a of negative 5, a of negative 1, and a of 2. And here I got a positive, a negative, and a positive. So what this tells me about what I want to do to see if we're slowing down or speeding up is I'm going to draw a double number line, because that's how my brain works. So I have a of t. I'm going to put my v of t on top, just so we're matched up. And I have critical numbers for both at 0, and then a critical number at 1 for v of t, and a critical number of negative 1.26 for a of t. So I just need to test every single interval where I have a change for either my velocity or my acceleration. So I'm going to look and be like, okay, velocity below 0, I am negative. The outputs were negative. So below 0, my outputs were negative. Then between 0 and 1, my output was negative. And then from 1 on, my output was positive. For acceleration, less than 1.25 is positive, and is it 1.25 or 1.26? Oh, it rounds to 1.26, so 1.25 dot dot dot. Okay, between negative 1.25 and 0, the output is negative, and then anything from 0 on, the output was positive. So I have positive. So I just look, where are the signs the same? That's where we're going to speed up. It looks like in this section from 1 to infinity. Okay. Or from the cube root of negative 2 to 0. And then we slow down when the signs don't match. So here, from negative infinity to the cube root of negative 2, or from 0 to 1. And that is it for today.